But one slide, I think I put too much things. So this talk is something very fundamental, and I believe it should be very easy to understand. And I have only 13 slides. Now this one is the second. Now 12 left. So whenever you want, you can stop me and ask me. Okay? And I have enough time. Small number of slides. Okay. So I believe I don't need to introduce the meaning of this simple conservation law. So everybody knows this. For example, if f is 1 over 2 u squared, this is just implicit Berg's equation. And people know that, okay, this one has a lot of weak solutions. And we always consider the right one, which is entropy solution. Sometimes we use that one viscosity solution. Okay. So we always consider meaningful ones. But this one has a lot of weak solutions. And okay, so U0, we want to consider just positive solutions, and which is with the bounded initial value. In a special case, when the flux F is convex, then it's well known that the solution satisfies this Oleinik type inequalities. And so in some sense, the wave speed, the derivative of wave speed is bounded above, and this is a one-sided estimate. And sometimes we can rewrite this one in this way. Okay, that's the same thing, right? Derivative, okay, put this thing here, that's the left side derivative, same thing. But sometimes people prefer to write things in this form. And we say this one is sharp. The sharp means there is a case, or there is a solution that satisfies equality. So that's a fundamental solution. So we say this one is gives you the sharp regularity. And this Oleinik estimate gives the boundedness of the total variation. So that's a very important feature of this simple estimate. And there are many, I told you there are many weak solutions of the problem, but the one that satisfies this one is unique. So the entropy solution, means the meaningful one, satisfies this inequality. And the one that satisfies this inequality is unique. So actually this one, you can easily see the last entropy condition from this relation. But this one satisfies when the flux is convex. If the flux is not convex, then in fact the meaningful solution does not satisfy this. So that's one thing. And in fact, what? Diffusive 83, he showed that the uniqueness, so this one gives uniqueness if and only if the flux is convex. So if the flux is not convex, okay, this is not satisfied. And even if you consider the ones that satisfies this one, the weak solution is not unique. So if without convexity of function flux F, okay, everything ruined. So it's very natural to try to find substitute. So what is the generalization of this kind of inequality without the convexity assumption for the flux function? Okay, so that's very natural. And some people consider some weaker form of the Oleinik type inequality. So the idea is this: the solution does not satisfy the extent inequality if F is non-convex. Then okay, try to find a weaker form which is satisfied by the solution. And the form is, and all the all the weaker form of the Oleinik type inequality is given in this way. So if C equals 0, okay, that's Oleinik inequality. Now we have some extra term on the right hand side. And this is, so definitely this is a weaker form. And the total variation of the initial value minus total variation at time t. So somehow, if you see this, okay, this is something some quantity too big, which is too big. So many people feel uncomfortable with this. And I told you that one of the main features of the Oleinik inequality is this. This one gives the boundedness of total variation. So that means even if your initial value has no boundedness, it gives you boundedness for the total variation. But if initial value is total variation of initial value is not bounded, okay, the right hand side infinite, okay, this makes no sense. And some people consider, that at least I can find these 4 papers and try to improve the constant C. So in some cases, these papers, 08, 04, 01, 86. And also, if this is a weaker form, then the solution that satisfies, the weaker solution that satisfies this inequality should not be unique. Right? Oleinik. So convexity is, if the convexity of F implies the uniqueness of this inequality, and if you give a weaker form of this one, okay, then it cannot give you the uniqueness. So somehow all this kind of effort does not have the spirit of the Oleinik entropy inequality. Okay. And if you look at some other kind of problem, not the conservational, but for example, if you consider the diffusion equation, or if phi is u to the m, okay, people call this one the Pearson medium equation. Then this one also has this kind of one-sided inequality that people call this one Aronson-Bennilan type inequality. And this one also plays the key role in the development of the theory. And if you consider the P-Laplacian equation, something like this, now phi is given in this form. And this one also has similar one-sided inequality. So people now call this one Aronson-Bennilan type inequality. And this plays exactly the same role of the Oleinik inequality for the conservation law. And these things are also sharp in the sense that if you put the fundamental solution in the place of u, equality holds. And some people try to generalize or try to obtain this kind of estimate for more general flux functions, not just power form, but some other form. But most of the cases, okay, they could not possibly obtain the generalized form of corresponding problems. And what I'm going to do today is to talk about a lot more generalized form of the equation, which can be written in this way. So this is a one-dimensional case. Later I'm going to talk about the n-dimensional case. So one-dimensional case, okay, consider some function f, some equation, and the right-hand side, the f is now depend on x, t, u, us, u double x. Initial value, positive, bounded. Now we call rho m as a fundamental solution of the same problem. So rho m is this. So m means the mass of the solution. So m times that Dirac measure is the corresponding initial value. And for example, all the previous examples can be written in this form, definitely. And then the Oleinik type inequality. Oleinik inequality is this one. And I told you that fundamental solution satisfies that equality. So you can write this. Or Aronson-Bandler type inequality for the porous medium, or Aronson-Bandler type inequality for the P Laplacian can be somehow written in these ways. Okay? So what's the point here? All of these inequalities actually a comparison with a general solution with a fundamental solution, right? So forget about this middle column. Then these are just the comparison with the fundamental solution. So if I wanted to make a generalization, then okay, so I thought about this one about 3 years ago, or 2.5 years ago. Then I knew that it should be some comparison between general solution and the fundamental solution. Okay. And if you look at this one, then somehow this inequalities says that the fundamental solution is steeper than any other solution. So that's the essence of all these kind of inequalities. So my generalization of this kind of inequalities for this a lot more general equation is somehow statement should be somehow fundamental solution is steeper than any other solution. Okay, so what sense? So how to phrase it? What's the essence? What's the best way to phrase it? That is this. So okay, here is the solution of this one. Rho m is a fundamental solution with mass m. So first, this u is just a solution. So initial value is just a bounded one. Okay, don't need to be L1. Then if partial derivative of f with respect to q, q is the last term. Okay, so differentiate f with respect to u double x. So with respect to q, and suppose this one is positive, and initial value is bounded. Then the point is this one, the set A. What's the set A? Rho m fundamental solution minus general solution u, and bigger than or equal to, or bigger than or bigger than or equal to 0. This is set. So that's a level set of difference of between the fundamental solution and the general solution. And this set is important, and claim is this set is connected for all t and for all mass m. Okay, that's my phrase of generalization. Okay? Then, okay. So, how can we, okay, let's make a picture. So in some sense, if like this is solution, general solution u at time, profile is a graph of general solution at time u, at time t, now that's the fundamental solution. Then here the set A is exactly this interval. This is set A, and claim that this is rho m, this one is u. And claim is this set A is always connected. Okay, first thing is to prove this one, but the proof of this one is very trivial. In one-dimensional case, we have general set theory or lambda number theory, or all these things actually means this. Okay, so let E is their difference, so the difference of this one. ET is okay, this one minus, so ET is rho minus E is rho minus U, so F of rho minus F of U. Now they write this, so this is rho U, so Okay, subtract, add. Okay, then equality. And we write this one in this form. Then this A is okay. We can write this B, C. Okay, so we can just simply rewrite this one. Then what? Assumption for F is this. The assumption for F is this. This one is, okay, so here just, okay. First, suppose the solution U, a fundamental solution, and F, consider the case when they are smooth enough. And this one, assumption is this one is bigger than or equal to 0, but assume this one is strictly bigger than some epsilon. So assume this one first, then if we write this, then A, B, C, and then A is bigger than epsilon, and all of this one is smooth. Okay, everything is fine. Then we can apply the zero set theory or lambda number theory. And what's the lambda number theory? Zero set theory. Zero set theory means that, okay, if there is a zero set, the number of zero sets decreases in time. So that's the zero set theory. Lambda number theory, okay, consider number of change of the monotonicity, and lambda number theory says that the number of change of monotonicity decreases in time. So okay, or you can rephrase that one, something like that. The connected component of this level set is decreasing, so they are equivalent. So okay, the theory is already there. I have nothing to prove. So the more important thing is for one-dimensional case. N-dimensional case, there is no such thing like zero set theory. One-dimensional case we have. Okay, so okay, take it. We have only the proof. So in this part, the important thing is what's the meaning of that connectedness of the set A. Does it give you what you want? Okay, that's the important part for the one-dimensional case. Multi-dimensional case, you have to prove it. So that's a completely different story. Now consider the case, autonomous case. Okay, let the right-hand side is independent of x and t. Now u, ux, u, double x. In fact, if this one has dependence on time variable t, that's fine. Important thing is it's autonomous case with respect to the space variables. So there is no x dependency in f. And same condition. Then, if there is no x dependency, if this is an autonomous system, if we translate the initial value, the solution is always translated. So, instead of the set A with the t and m only, we can also give extra freedom. So that x naught is in this way. So fundamental solution can be translated at any place. You can place fundamental solution at any place and consider this level set, and that one should be connected, right? So if we have this one, then since this one is autonomous system, okay, this one is free. But this is what I'm going to use, and this one gives you what you want. Okay, now let's check what the connectedness of the set A gives you. First, connectiveness actually gives you the stiffness. Okay, let's share. This is a graph. Let this solid lines are the graph of fundamental solution. Now the started line is the graph of general solution. Now, okay, here is a fundamental solution. Like this, here is some general solution. I want to compare the values, the point, with the same value. Then I can translate fundamental solution at the same place and then compare what's happening. So, okay, these are the pictures. Then, four possibilities. When this one may cross in this way, or in that way, or tangent in this way, or tangent in that way. There are only four possibilities. And the theorem says that, so we can easily show that First, this is not possible always. This never happens. That's one. And these two, if we take m large enough such that maximum of the or maximum of the fundamental solution with mass m is bigger than the maximum of the solution, right? So the solution U is bounded one, so we can always take m large enough such that in this way. Then with that m, these two are not possible. Okay? So this is always false. This never happens for any m. If m is large enough, okay, this does not happen. Okay, of course, it depends on your equation. In some equations, this is not possible for any m. There are many systems. But we are talking about generality of this kind of, okay? And with this kind of system, always you can say that never happen. These two, if m is large enough, this never happen. Now, proof. Okay, I'm going to prove this one. Just waving my hands. So we know that set A is always connected. Okay. First, show that this is not happening. Okay, so we can always translate fundamental solution. So translate fundamental solution. This is only the one, just a little bit on the right-hand side. Then why the set A becomes disconnected. Okay, so never happen. Okay. Now let's say this one. So if this one is true, then the maximum of solution U cannot be bigger than the maximum of this fundamental solution. So if you graph it, it should come down. Right? That means set A becomes disconnected, right? Set A is this part and that part, so it should disconnect. So this never happened. This one is still same. Okay. For here, move this fundamental solution left-hand side a little bit, then there is some component here. Now maximum of this one should be smaller than the maximum of the fundamental solution. So this one eventually goes down. It goes below the fundamental solution. So the set A becomes disconnected. So this never happened. So you can clearly see that this never happened under this condition. This never happened without this kind of condition. Okay? So this one says the connectedness of A implies the steepness of the fundamental solution. So always like this. It always close in this way. So it cannot be steeper. Okay, that's the theorem 3. And I believe I roughly proved this one. Now regularity. So if you have now, even if I make the graph something like this, some cases solution may have discontinuities. So conservation law is a very good example that the solution may have discontinuity. I'm sorry. I forgot to mention one thing about the proof of this. Here when I prove this one, I assumed the smoothness and this kind of thing. And for more general case, for a general case without the smoothness, we may take a perturbation method with a small linear division, add some small linear division, and smooth some kind of use the interpolation for the flux F and make it C infinite, and then take the limit. So then in that way, of course, to do this one rigorously, it needs some work and some theory, but that's completely doable. And that kind of approach is very classical. Okay, that's one thing. Okay, this I mentioned this. Now here, for convenience, I made the graphs as a continuous function, but this one may have discontinuity. Then regularity study, regularity and uniqueness for the conservation. Now, okay, conservation law. So conservation law is a very good example that give you discontinuous solutions. If the flux is not convex, then the discontinuity can be very there can be very different kind of discontinuity, increasing one, decreasing one, contact discontinuity, and yeah. Then, for example, the fundamental solution has this kind of discontinuity. Then, okay, the general solution, so corresponding graphs, corresponding to this kind of graph, with the discontinuity is these four. And similar, so this never happened, this does not happen for m large. Then, okay, what's the uniqueness? Does the connectedness of set A gives you the uniqueness of the weak solution? That, yes. Why? This kind of, if this is fundamental solution, that's an admissible one, then this discontinuity is admissible. And if this continuity is smaller than this one, okay, that discontinuity should be admissible. So somehow here you have to know the theory like the Oleinik entropy admissible criteria. If you know these things, then okay. This one says that if this discontinuity is admissible and this is a smaller one, that one is admissible. So these are not admissible. So always this is the case. That means if you have solution has a connected, set A is connected for all m, for all time, and for all place x now, then that means okay, this is the only case with the discontinuity. So all the discontinuity is acceptable. That means that gives you the regularity, and that gives you the uniqueness. How about the regularity? For any case, if the fundamental solution is continuous, then the solution U always continuous. All right? And so, okay, so this theorem is not just for this case. This theorem is for the general case, and this one says that sometimes fundamental solution is discontinuous. Then, okay, the general solution can be discontinuous. But somehow you found that your fundamental solution of your problem is always continuous for all time t. Then your general solution, even if the initial value is very weird, your general solution should be continuous immediately when if t is bigger than 0. Okay? This one is also clear, right? If general solution has discontinuity, then that is of this case. Okay, but this case is not possible. If so, we have regularity. So one of my plan is to talk about a little bit of the asymptotic behavior, or show the asymptotic convergence rate for the nonlinear diffusion equation. That one was the part of my original title, but somehow this is the one. Now, if you want to use this kind of theory or this kind of argument to show the asymptotic convergence order, then the equation corresponds. So you have to restrict your equation a little bit more, something like that. The equation should be in a divergence form. If that equation is divergence form, okay. So one thing, this equation. This is general, so there can be some reaction term, or so there can be some source term, and the solution may increase, all right? But in that case, okay, I don't know what's asymptotic. Probably we don't have asymptotic convergence rate. But now restrict that one to this kind of equation, then we can obtain some convergence order. So in this case, basically the solution. Total mass is conserved and the solution somehow decays. So if there's a fundamental solution, this one is the general solution. Now this U has a compact support and total, so bounded and compact support, then okay, total mass is finite. Then with this M, okay, compare these two, and the L1 convergence order is of order of the size of the fundamental solution of the, right, as t goes to infinity. So if we know if you know the rate of the decay rate of this fundamental solution, then you obtain this the convergence order in L1 mode. Okay. So actually this is the okay. There are a lot of studies for the intermediate asymptotics for this kind of equations. Okay, for many different cases. I believe this is the most general one. And actually, all of this study started to do this kind of thing. I started to obtain the convergence rate of this kind of problem, and somehow this one give you all this kind of stuff. And now it look like minor. The other thing is better. Okay, so all those fields are the one-dimensional case. But multi-dimensional case is a lot more challenging. Conservation law in hyperbolic system, basically they are a one-dimensional property. So something is flowing. So if you change the variables, make all the flat, then basically hyperbolic structure is a one-dimensional structure. But the diffusion, that's different, of course. Now for the multidimensional case, we make, okay, so may consider this one. X, T, U, the same thing. Now this is a gradient, this is Hessian. So suppose equation is given in this one, and the U is what? Bounded, it's the same, and positive equals the positive solution. The rho m is a fundamental solution, so something like this. Then what I expect, or what I want, is this. Let this n by n matrix, so partial derivatives with respect to the last component, Q. So it's the n by n matrix, so you have n by n matrix here. And if this one is positive definite, okay, if that one is positive definite, then the corresponding set A, this one, okay, the same set, is simply connected. So that's what I wanted to prove. Do I have proof? None yet. But this one is the corresponding concept, but very natural concept, right? And for one-dimensional case, the connectedness of one-dimensional case simply connected or connected, that's the same thing. But multi-dimensional case, they are different, right? So the what I want is simply connectedness, simple connectedness of this kind of set. And multi-dimensional case, this one will play the role of all the estimates, Oleinik time estimate or Arrow's-Mandela time estimate. So we just saw that for the one-dimensional case, the connectedness of the set A gives you many things. This one will give you many things. But first, I should have the connectedness first, right? And yeah, as I mentioned to you, there is no such thing like a zero set theory. So, okay. So for example, this one is just a general solution V. That's another general solution U, and consider the set, this kind of set. Then this one may have many connected components, and the zero set theory should be like this: the number of connected component decreases in time. If we have that kind of argument, okay, everything is done. But that is not. We don't have that kind of theory, and that is not even true. That's false. Sometimes, multidimensional case, the number of connected components may increase in time, depending on the structure. Eventually, it will decrease. But at such a time, it may increase, depending on the structure. So proof is very different, or it's somehow. So the dimension effect, that's a really serious problem when you want to obtain this kind of thing. But if this is not the general solution, this is fundamental solution, okay, then the set of this one. I believe this one is simply connected. Do I prove? No. But I have this heat equation case. So the last one. The heat equation case. So okay, let's try to the simplest case. Heat equation. General solution. Initial value bounded. And fundamental solution with mass m. So let's phi is this heat column. Then, since this is a linear, this fundamental solution is just m times heat column. It's just that. The set A, okay. Heat equation, okay. This is not just simply connected. This one is actually convex. It's a better structure. This one is convex. So possibly this one is convex. I don't know, but at least this one convex. Proof, very simple. I prove only the simple things, not complicated. Okay, so I want this one. Then put psi as the ratio, divide this one 2. Then the set A, same as this. The ratio bigger than or equal to 1. Okay, right? Then this one. Put this thing here, divide both sides by this, then we have this. The opposite. Like this. Here is 1. 1 is should be bigger. Okay. Oh, so in my final time, there was but yeah. So inequality is opposite. This one is the other side. Then okay, rewrite this one. Then we know the exact solution. Exact solution is just the convolution with the initial value and integration. Now rho m is here. Put this thing at the bottom. Now this one is the Gaussian. Now this one can be cancelled, right? Bottom thing is cancelled with all these things, and this is written in this way. Alright, put here x minus y, here x minus y, then that's the dot product with the x minus y, dot product of x minus y, x minus y. Then expand this one, then cancel with this one, then only this term left. Okay? Now differentiate this one with respect to xi twice. Then where is xi? Here is xi. Here is x. So 2yi comes out with 4t. So to differentiate twice, that takes care of this. So this one is positive. Okay, we consider positive initial value. All these functions are positive. Okay, everything positive. So second order derivative is positive. So psi is convex if you restrict on any single line, right? So here, consider the xi-axis, or parallel to that one. That's always a constant. And so if you consider some kind of rotation property, so equation is invariant under rotation. So if you take any line segment, and if you restrict psi on that line segment, then your solution is convex on that one. So that means the set A is actually convex, right? If set A is not convex, then consider some line segment. On the line segment, psi should be convex. So the corresponding set A on the line segment cannot be disconnected. Okay. So the set A should be convex. So at least for the heat equation case, okay, we know that this one is convex. For more other cases, for more general cases, I expect this kind of thing. So okay, this one is an ongoing project, and then the first thing is okay to show the connectedness for more general case, and apply this one to give many other kind of estimates. So that's the project of this one, and I'm very glad I get the attention from you. Thank you.
You have any question or comments?